Hi, I'm Nick Letherby, the IoT Ecosystem Manager at Texas Instruments. I'm giving a 5-part training series entitled Understanding Secure Connectivity in IoT and Embedded System Devices. This is the 5th module in the series entitled How Do Common IoT Software Applications Use Cryptography? And we're going to walk through a number of software functions such as establishing a secure network connection using TLS, performing a secure remote update, performing secure provisioning of security credentials to an IoT device, and then finally look at how many certificates are needed on an IoT device. You may find that it helps to take the earlier modules to fully understand some of the terminology and technology discussed in this particular module. To give you a better perspective of all the cryptography and security concepts you've learned in the previous modules, we're going to walk through some examples of how cryptography and certificates are used in real-world software. The first example will walk through how a TLS connection is established. Then we will look at how an IoT endpoint can be provisioned with a certificate using a certificate signing request. Next, we'll look at over-the-air updates, which is how you can securely perform a remote update to a IoT endpoint. Then finally, we'll look at all the certificates required in an IoT endpoint to make sure you have a good grasp of different ones needed in the endpoint. Before we get into the details of exactly how the TLS protocol uses the various cryptographic concepts we've discussed in earlier modules, I'd like to talk a bit more about TLS itself for those of you who are not familiar with it. TLS is the standard protocol that's used to provide end-to-end communication security over the internet. If you think of an HTTPS server, it's simply an HTTP server that also uses a TLS secured connection. Now, if you're not familiar with the acronym of TLS, you may be familiar with something called SSL, or Secure Sockets Layer. And SSL was the predecessor to TLS, and it was replaced by TLS back in 1999. However, because there is a popular implementation called OpenSSL for TLS, a lot of people are still more familiar with the term SSL. What we're going to do in this presentation is walk through the handshake for TLS 1.2. This is the most widely deployed version and one used in today's IoT implementations. This handshake will show how all various security mechanisms are used that we've discussed earlier in the presentations. Now, there is a more recent TLS standard called TLS 1.3 that came out in late 2018. It does optimize the handshake, so the handshake is a little bit different, but the same security principles apply. The other thing that TLS 1.3 does is it removes support for many older ciphers that have compromised security. And if you reviewed some of the earlier modules in this class, you'll notice that we specifically talked about ciphers that would be used in TLS 1.3 going forward. However, TLS 1.3 hasn't even been deployed yet by major IoT services, so we believe discussing TLS 1.2 in more detail is the preferred option at this time. Before we go into the details of the TLS handshake, I would like to make one additional point. If you search for explanations of TLS handshakes on the internet, you'll typically find ones that discuss only server-side authentication. This is because when a browser connects to a large public website like Google or Facebook, those websites don't care about who is connecting, and therefore there's no need to authenticate them. In an IoT network, the situation is different. You don't want any old device that will connect to your network. You only want devices that are authorized to connect to your network actually being connected. Therefore, client-side authentication is enforced, and our discussion of the TLS handshake here will include client-side authentication. Let's start with a very high-level view of the different stages of the handshake. The first stage is something known as the client and server hellos. There are no cryptographic techniques applied at that stage. The purpose of this stage is for the client and the server to agree on which ciphers they'll actually be using and also to exchange the certificates for mutual authentication. The next phase is authentication, where the certificates are taken and validated by both parties. Obviously, this does involve quite a bit of cryptography, including asymmetric encryption and digital signatures, public key infrastructures, and certificates. The third phase is key exchange, where a symmetric key is exchanged between the two parties. To exchange this key, asymmetric encryption and digital signatures are required. And if you recall our discussion in one of the earlier modules about Diffie-Hellman, you'll probably recall that the actual key is not exchanged. The value is just in parallel generated by both parties. And finally, at the conclusion of the handshake, both parties switch to the agreed symmetric encryption cipher and the key they have just exchanged to begin normal encrypted data exchange via messages. The first message sent, which concludes the handshake, is a hash to the whole handshake, so each party can check that no attackers successfully compromise the communication at any point. Now let's start walking through each of these stages in more detail. The first step in the handshake is the client and server hellos. It's the client, i.e. the IoT endpoint, that will initiate the connection to the IoT service, and it begins by sending a TLS client hello. This contains a list of the supported cipher suite in order of preference, a list of the supported TLS versions, and also a random byte string. The IoT server will then respond by selecting the cipher suite, and it will select the strongest possible from the list presented to it in the client hello. It will then select the latest version of TLS that was available in the client hello. At that point, it will do a couple of different things. It will send a session ID down to the client. It will send its own random byte string, and it will send its certificate chain along with a request for the client to send its certificate chain. The random byte strings we see exchanged here will be used later to compute the shared symmetric encryption key. Before we go on to talk about the next step in the TLS handshake, I'd like to explain the actual cipher suite strings in more details. It's often confusing when you actually start looking at the TLS API calls as to what's happening. I've given an example here of a typical TLS 1.2 cipher suite string, and you'll see it basically has three components. On the left-hand side, the ECDHE_ECDSA refers to the key exchange algorithm that's going to be used to share the symmetric session key between the client and the server. And then it also refers to the digital signature algorithm that will be used to help authenticate the key exchange. The next part of the string with AES 256_GCM refers to the symmetric cipher that will be used for encrypted communication once the secure connection is established. So AES 256 is the symmetric cipher. Then the MAC or tag for the message that's used to authenticate each message in the stream is specified here by GCM, Galois counter mode. Then finally we have the actual hash function, also referred as a pseudo random function, and that can be used in a number of ways. It's used by ECDHE during key generation, and it's also used by DSA to generate digital signatures. Finally, if you're using a different type of MAC function, GCM does not need a hash, but there are other MAC functions that do require a hash. If you selected one of those, then it would use SHA-384 here to help generate the MACs. One thing you may have noticed is that none of these ciphers are associated with the certificate authentication. And if you recall a certificate includes the information on which cipher should be used for its digital signature. So therefore that's independent of this cipher suite list. The next stage in the TLS handshake that follows the client and server hellos is authentication, where the client and the server authenticate each other. We're just going to cover the server being authenticated by the client, since the server follows the same process when authenticating the client. The authentication process starts when the server sends the client, which is the term we'll use here for the IoT device, its certificate chain. The client will then validate the certificate chain. It will need to have the trusted root certificate installed on it to complete the validation. As we pointed out earlier, this might be in a certificate store for a more memory-rich client, or it may have specifically been loaded into memory for clients with limited amounts of on-chip memory. Once it's checked the certificate chain, the next thing it does is look at the certificate expiration. It compares the expiration date versus the current date and time, which it fetches via an NTP service, such as one operated by Google. If the certificate has not expired, at that point it can just simply complete the authentication. However, in some cases it may do something called checking for certificate revocation. The certificate that the server sent may subsequently have been found to have been compromised. To double check this, the client needs revocation status. It can either go out and request this over the internet, but more commonly there's a technique called OCSP stapling, where the IoT server will have already provided the revocation status stapled to the initial certificate chain. The client can then check if the certificate's been revoked. If it has not, it can assume the certificate is valid and then proceed with the rest of the communication. Following these three steps, the client can now be sure that the server's certificate is in fact valid for use. There is an additional step that needs to be done. We'll cover this in the next section, but essentially the client at this point doesn't know if the server owns the private key associated with the public key in the certificate. So in the next step, what will be done is for the server to encrypt some data that the client knows about with its private key, send it to the client. The client will then decrypt it and match it with its version of the data. And if these match, it now knows that the server does in fact own the private key associated with the certificate and can be trusted. As I mentioned at the start of the slide, when a server authenticates the client, the steps are essentially the same. The one potential difference is that an IoT server may well have a list of client certificates that are valid for its IoT devices, and it will likely check against that valid certificate list rather than explicitly checking for revocation, for example. Once the certificates have been authenticated, the next step is key exchange. And to remind you, what we're doing here is we're going to actually calculate the shared symmetric key that both parties will use for the main part of the communication throughout the rest of the session. The key exchange begins with the send server key exchange message. This sends over the server Diffie-Hellman parameters. In addition, if we go back to the previous slide, I discussed how the client, for example, needed to be sure that the server actually owned the private key that was associated with the public key sent in the server certificate. That's done in the send server key exchange message. So the server generates a signature from the previous handshake traffic, and obviously that signature is simply encrypted, hash the previous handshake traffic. When the client receives that, it can then take the public key in the server certificate it received, decrypt the hash, and then compare it with the hash it generates itself for the previous handshake message, or the previous handshake message traffic. If these match up, it then proves the server owns a private key. At that point, the client will then send its key exchange message, which of course will include a handshake of the previous traffic as well, in the case of client-side authentication, and its Diffie-Hellman parameters. If you're not familiar with Diffie-Hellman, please refer to the previous module on certificates and the module before that on asymmetric encryption, and this will explain how Diffie-Hellman works in a little bit more detail. So at this point, both sides have the Diffie-Hellman parameters, and if you recall, in the client and server hellos, they both exchanged random byte strings. At this point, both parties can independently calculate a shared secret key using the Diffie-Hellman parameters and the random byte string they received from the other party. There's several stages involved in this, and I'm not going to get into those stages. They involve pretty complex mathematics. But the result of the key calculation is, at the end of that process, both sides have independently come to the same shared secret key value to begin communication using symmetric encryption. At that point, the client sends a client change cipher message. The change cipher message will tell the server to change to the previously agreed symmetric encryption protocol, such as AES 256. In addition, the client finish message includes a hash of the previous handshake messages. The server can compare this to a hash of its record of the previous handshake messages to make sure that no attacks occurred at any stage of the handshake. At that point, the server obviously changes to using the symmetric encryption protocol agreed for the rest of the session, and it sends back its change cipher message and its server finish message, so the client can again verify that there were no successful attacks during the exchange. Once the TLS handshake is complete, the session can then proceed with message exchange between the client and server. This is a very straightforward process. The client will simply encrypt a message with the shared session key and send it to the server, which then decrypts it with the shared session key, and vice versa for messages from the server to the client. A couple of points to make are the session key is not stored permanently, and that's one of the advantages of the ephemeral Diffie-Hellman implementation that's now standardized for TLS. It means that a new session key will be created the next time the client and the server connect, and that means that subsequently getting hold of the key for a later session does not enable you to decrypt earlier sessions you may have recorded. And again, if we go back to our discussion a couple of modules ago about symmetric encryption, symmetric encryption includes a message authentication code, or MAC, which is used in each message to make sure that an individual message cannot be altered or tampered with by a third party. So that concludes the discussion about the TLS handshake. We're now going to move on to talk about a certificate signing request. The use case we're going to cover for a certificate signing request, which we're going to abbreviate to CSR in the rest of this section, is how to use one to join an IoT device network. Earlier in this series, we've pointed out how IoT device networks are closed. They're not open servers like Google or Facebook that allows any client to connect. They only want authorized IoT endpoint devices to connect to them. And to enforce this, the IoT endpoint device must have some type of security credential, which will typically be a certificate if the IoT network is using something standard like TLS authentication. If the IoT device has its own public-private key pair, it's possible for the IoT device to generate a CSR and get the certificate delivered at runtime rather than having to burn it in directly in the factory. The advantage of getting the certificate at runtime is reduced costs, because managing certificates and the associated private keys during manufacturing means you either need an expensive, secure manufacturing location, or you need to have a third party create a series of secure elements that contain pre-burnt certificates that can then be used at a low-cost manufacturer. Either of these approaches adds cost, and therefore it's much more desirable to add the certificate during, for example, product installation. However, the way CSRs work means that you have to do a little bit more than just a simple CSR to guarantee only authorized devices can join the network. And to do this, it's very useful if the IoT device also has a unique identity that can be used with the key pair to help verify its identity. To enable the device identity to be confirmed prior to issuing the CSR, it's necessary to have a database that matches a device ID with the public key value that the device will have in the certificate. Each IoT endpoint device will need to have a unique identity. This may be an immutable identity that's already present on the device, either in a secure element or in the MCU itself, or it could simply be added as a label on the box the device ships in. In the case of the unique identity being on a label, it will be necessary for there to be a phone app for the user to enter the unique device identity during installation so that the device can use it. The IoT device vendor will need to create a database that stores both this identity and the associated public key that is stored on the endpoint device. This database can come from a couple of sources. Semiconductor vendors who provide secure wireless MCUs or secure elements may provide a whitelist that contains the public keys and associated identities. This may come with certain volume requirements, such as a minimum of 2,000 devices. Another approach is simply to generate the database during test. For example, when the IoT endpoint device is being tested, it can be booted up and some code can be used to extract the public key and the identity, and then it can then be stored in a database that can be used for future reference. Now we've described how the actual database that will be used to verify the IoT device identities is created. Let's actually look at the process of the CSR being generated and then the provisioning service verifying it's a legitimate CSR. So if we look at this diagram here, we'll see we have the IoT endpoint device, and the user will connect that up to their home network and begin the installation. Once the IoT endpoint device is connected successfully to the Wi-Fi home network, it can now generate and sign a CSR, and this CSR will include the identity that's unique to the endpoint device, and also will include the public key. This CSR is now sent to the provisioning server, which we've called the registration server here. And goal of the registration server is to validate the device's identity, and it does that by referring to the identity database we described in the previous slide. So you'll see here that the CSR comes in, the provisioning service will extract that identity from the CSR and the public key, and then compare it to the entry in the database. If there is a matching database entry that has the device ID with the same associated public key, it knows it's an authorized device, and at that point it can then pass the CSR onto the certificate authority server. The certificate authority server will now then issue the client certificate back to the IoT endpoint, and that will then store that certificate. It should store it in a secure manner so it cannot be accessed by unauthorized parties. Now that the IoT endpoint device has the client-side certificate, it can now simply open a TLS connection to the IoT network, which of course requires client authentication, and then it simply passes up the client certificate during the authentication process, and the IoT service will permit the device onto the IoT network. So you'll see with this approach that there was no need to actually pre-program the certificate into the IoT endpoint device. It simply went out and got it during installation. And this greatly simplifies the production process for IoT devices. A third common application that involves use of cryptography is secure OTA updates. OTA stands for over the air and can really be effectively regarded as remote updates. Virtually every single connected embedded application is going to want to do remote updates. There are several reasons why this is so. First, it's much cheaper to remotely patch bugs or security vulnerabilities in an embedded application via a network connection than have technicians physically upgrade each individual system. Secondly, you're going to want a cheap way to replace expired or revoked certificates, which again feeds back to improving the security of connected devices. And then finally, it may be a good way to boost business by adding a new service to an embedded application that generates a new revenue stream. So the ability to do OTA or remote updates is extremely critical for any modern IoT application. However, security is very important because since the OTA mechanism is actually downloading a new image, if an attacker can subvert that mechanism, they can therefore take control of the device by installing malware. So, cryptography obviously has a key role to play in OTA. Now, unlike secure connectivity, where there's standards like TLS that prescribe how to perform a secure connection, there is no specific protocol that governs an OTA process. So what we're going to do here is walk through an implementation of an OTA process that does deliver security. Now, of course, secure OTA requires a secure TLS-enabled connection. But in addition, it also requires another certificate called a code signing certificate that's used to authenticate the image. Before we get into the specific steps of performing a secure OTA update, there's a couple of security risks I'd like to highlight. One is fairly obvious. Since the IoT device endpoint is expecting a new image, an attacker can try to substitute their own image so they can perform a malware takeover of the device. The second form of attack is called a downgrade attack. In this case, since the OTA device is looking for a signed image, it's not possible to substitute a random malware image to do the takeover. However, if the attacker has obtained an earlier OTA update image with a known security vulnerability, they can send the device that image in the hope they can downgrade the device to this older version of software that can then be exploited by another form of an attack. So, how do we go about countering these security threats? The first step is to create a digital signature that we can use to sign the image. To do that, we would simply take the OTA update image, create a hash, and then we encrypt it using the private key of the code signing certificate to create the signature. By signing the image, we make it impossible for an attacker to pass malware via the OTA mechanism and then have that malware accepted as an upgrade. Now, of course, simply signing the image doesn't address the downgrade attack approach. To counter downgrade attacks, it's useful to add metadata. Obviously, one extremely important piece of metadata is the actual version of the software image. So if we append some metadata to the image prior to creating the signature, at that point we'll have a version associated with the image which will prevent a downgrade attack from happening. It's also worth including other types of metadata such as the applicable product part numbers. These are helpful to prevent reliability problems in the OTA process that can end up bricking the endpoint. And we'll discuss reliability in a little bit more detail later in the OTA discussion. Once a signed OTA image is available on the OTA update server, the next step is to have the IoT endpoint device download it and then authenticate it. On the IoT endpoint device, there will be an OTA agent, and this will periodically monitor to detect if there is a new update available. If a new update is available, the OTA agent will establish a secure connection to the OTA update server using TLS, although in some cases the OTA agent may simply use the existing telemetry channel to perform the download. It then downloads the image and metadata and signature into temporary files. The IoT endpoint device will already have the public key from the code signing certificate burnt into it during production. It uses that public key to extract the hash from the digital signature. It then takes the downloaded image and generates a hash for that and compares it to the hash from the signature. If these match, it knows the image is valid. At that point, it will check any metadata such as version numbers, and if the version number of the downloaded image is later than the one that's already on the IoT endpoint device, it knows it can safely upgrade and is not suffering from a downgrade attack. The final step is to boot the new OTA image. The booting process should incorporate a number of checks to ensure that it works reliably and securely. The bootloader should be secure. By a secure bootloader, I mean the bootloader should check the signature of the image to authenticate that it comes from the device provider. While of course we've already checked the image signature when we did the download, having the bootloader also check this is important because it's conceivable that physical attacks on the device might attempt to replace the image in the device with a malware image by inserting, for example, a new memory chip. And in that case, secure boot would prevent this from being successful. In addition to checking the image is signed, you also need to be concerned about reliability. You certainly don't want the OTA boot process to hang the device and render it non-functional to the user. So a few procedures should be done to prevent this. One is that device should have enough memory that you can keep the prior image version available on device. And if the booting of the new image fails, you need to be able to revert back. To prevent a hang from happening, you need to set a watchdog timer, and that will time out. So if you do hang, the watchdog will trigger, and then you can then again revert to the previous image. So if we look at, see what happens here, the bootloader will check the signature and then set various flags in the watchdog. It will then boot the OTA image, run through a self-test, and if the self-test fails or the image hangs, or you have, for example, run out of battery and the device fails, all of these will simply result in you rebooting the previous old image that you know works the next time around. If, of course, you successfully pass the tests, at that point you'll stop the watchdog and then set the OTA image to be the new image that the device always boots from. It should be clear by now that certificates are a key element in providing secure connectivity between an IoT endpoint device and the IoT servers. With that in mind, I'd like to summarize exactly how many certificates are needed down on an IoT device to securely connect and perform secure OTA operations. This particular walkthrough will be based on a Texas Instruments CC3235 Wi-Fi MCU. It's an ARM Cortex-M based MCU with a dedicated Wi-Fi network and security processor. One important point is that the trusted root catalog that is programmed into the CC3235 only contains hashes of each certificate. This is because the CC3235 is an MCU with limited on-chip memory, and it's not possible to load every full certificate into memory without taking up an inordinate amount of space. When establishing a secure TLS connection, the first action the device will need to do is to authenticate the IoT server. The IoT server will send down its certificate chain. The CC3235 will need to contain the trusted root for the server certificate. That means the IoT device manufacturer must pre-program the trusted root certificate into the device. Because we're dealing with a closed network, the IoT device manufacturer will know in advance the trusted root required for the server certificate. The IoT device will use the hash in its trusted root store to verify that the trusted root programmed into the device for the server certificate is in fact valid. The next step in establishing a secure TLS connection between the IoT device and its server will be for the server to authenticate the IoT endpoint device. This requires that the IoT endpoint device can send a copy of its client certificate chain. The certificate chain will obviously contain the TLS end entity certificate and whatever intermediate root certificates were used in issuing that end entity certificate. Because the server will have an operating system like Windows or Linux, its trusted root store will certainly contain the full trusted root certificate to complete the client certificate validation. For the IoT endpoint device to be able to authenticate a signed OTA update image, it must be able to validate the code signing certificate. In the case of the CC3235, there's a requirement that a complete code signing certificate chain be present for the image to be authenticated. So in this case, we need to have the code signing certificate chain, including any intermediates, and the trusted root for the code signing certificate to be all present on the end device. It should be stressed, however, that many IoT device vendors are happy with simply putting the public key associated with the code signing certificate on the IoT endpoint and just using that and not doing a full certificate chain validation. Remember that OTA does not have any formal protocol associated with it, unlike TLS. So therefore, there is flexibility in how you implement this. So let's summarize how many certificates are needed. We need 2 trusted root certificates. One of these is the trusted root for the TLS server certificate, so we can do the authentication of the server certificate. We need the complete TLS client certificate chain, but not its trusted root, since that will be stored on the actual IoT server that does the authentication of the client. For a device like the CC3235 that wants to see a complete code signing certificate chain, that whole chain, including the trusted root, needs to be also on the device. However, since there's not a standard protocol enforcing this requirement, on some other devices you may be able simply just to put in the public key for the code signing certificate to authenticate any images downloaded for update purposes. In this module, we walk through several use cases where encryption is used in common embedded software applications. The first of these was TLS, which is the standard Internet Security Protocol. We went through the handshake and showed multiple use cases of asymmetric and symmetric encryption and how they're used to establish and maintain a secure connection. We then looked at OTA downloads and how encryption helps with signing images to make sure that only authenticated images are accepted by the IoT device. We also looked at a certificate signing request and how that can be combined with a unique device identity to create a secure runtime provisioning implementation that avoids the need to have certificates pre-programmed into embedded devices in production. We then finished by recapping how many certificates you actually need on an IoT device to make sure that you have a clear understanding of what is required for secure connectivity and OTA. This is the last module in the Understanding Secure Connectivity training series. If you stay with us with the next slide, you'll see a number of options where you can actually delve into hands-on training using a TI Wi-Fi MCU. Thank you for taking the time to listen to this series of training modules, and I hope it was helpful in understanding security-related technology. At some point it's likely you'll want to do some actual software development of a secure connected application. I've put a few links here to enable you to get the appropriate software and evaluation modules to develop secure connected applications on a TI SimpleLink Wi-Fi device. We have an extensive set of hands-on training modules called SimpleLink Academy, and if you go there and select, you'll see a number of examples that deal with secure connectivity, secure storage, and cryptography.